So today we are going to start lecture 49, and here I am going to discuss about some ways to build experimental designs which have more number of points than the ones we have discussed in the past. That is the typical 2K, the CCD, the FCD, and so on. And there are several ways to enhance these traditional experimental designs which we are going to discuss today. And again, this is lecture 49 in our optimization series, and I am Dr. Ranjan Ganguly. Now we have studied experimental designs such as CCD, and we have also mentioned that these are widely used in response surface methods in optimization. Now, one more approach is to use the so-called 3K design, 3 to the power K. And this 3K design results in a more intense sampling of the design space compared to CCD and 2K. So let's look at the 3K design. This is also known as the 3-level factorial design, and that's what the 3 here stands for. And essentially, whereas in the 2K design we have the low and the high level, in the 3K design we partition the space into low, medium, and high. And this medium is new with respect to the 2K design. Now, if you recall the 2K design, we had coded variables -1 and 1, which essentially referred to the low and high points in the design space. Therefore, we can consider the medium point to be the coded variable 0. And then we have essentially 3 levels, -1, 0, and 1, where 0 could be the baseline point. Now, if you want to pictorially look at the 3-level factorial design, we can consider the case of two factors or design variables. So we have x1 and we have x2. We have k equals 2. So the 3K design would be 3 to the power of 2, which would be 9 points. So you can see here the 3K design. And essentially now if you look at each variable, let's say x1, you have 3 levels. You have a high level, you have a medium level, you have a low level. Similarly, in the x2 direction, you have a low level, you have the medium level, and then you have the high level. So this is how we essentially partition this design space, and we create this particular design here. Now, of course, you can visualize this in higher dimensions. For example, if you had k is 3, you would have a cuboid type of situation, and you would have these designs filled up there. So that would become a 3 to the power 3 design. Now, one of the things we are going to see is that if the value of k becomes large, the 3K design essentially requires a gargantuan number of points. And that can be useful in certain situations where you are dealing with cubic response surfaces, 4th degree response surfaces, 5th order response surfaces, and so on. Now, if one peruses the literature, one does come across papers where people have used cubic, 5th, and such response surfaces. And these are typically for functions which are quite nonlinear. And here people try to develop response surfaces which are more global in nature, and therefore they span a large amount of the design space. Now, how do we get so many points in the 3K design can be clearly seen from this table here. So here I have a set of values of k. I have the number of regression coefficients for a second degree model or a quadratic model, and then I have the number of runs in a 3K design. So say k is 2, then I have 3 squared, that is 9. If k is 3, I have 3 cube, that is 27, and so on. And here you can really see the curse of dimensionality taking place, in that when k is equal to 10, you have a plethora of points. You have actually 59,049 points. So there is a veritable explosion in the number of points as k goes up. Now this of course may be a problem in some situations. It's quite difficult to consider this kind of a design when you have a very large number of design variables. But if you have a lower number of design variables, like something like 4, it's certainly feasible to use the 3K design. Now, one can think of a similarity between the use of higher degree polynomials in the response surfaces as well as retention of higher degree terms in a Taylor series. So if you recall, in a Taylor series you typically truncate the terms to quadratic, but you could always keep the cubic terms, quartic terms, fifth order terms and so on if you wanted to, and that would give you a good measure of the neighborhood compared to the point at which you are at. So for example, if we extrapolate that kind of thinking to response surfaces, we would get a third degree response surface in this form. So you have our usual familiar beta 0, beta 1 and beta 2, the linear model, you have the quadratic model here, the interaction terms and the curvature terms. And now you have some more terms. You have cubic terms, you have terms involving x1, x2 square, x1 square, x2, and so on. So the inclusion of these terms creates more regression coefficients which need to be found, and therefore you need more points in the design space at which you do the sampling in order to obtain the curve fit, and therefore in these situations the 3K design may be useful compared to the CCD. Now it is possible that you may use terms beyond cubic, and like I mentioned before, people have used quartic polynomials, fifth order polynomials and so on. And in those cases also you may be able to use the 3K design. You can get a more correct estimate as far as regression coefficients are concerned if you have a plethora of points in the design space. People have used designs such as 5K, for example, where you have 5 levels. And here you can picture these levels as being high, low, medium, as well as 2 levels between medium and high and between medium and low. So again, you could conjure up designs such as 7K, 9K and so on. You could have a plethora of points spanning the design space. Now, instead of doing something like that, a different approach which is probably better is what is known as progressive lattice sampling. And in this, the number of points in the design space are slowly brought up. So you start with a certain design. For example, we could start with a 2K design. So if we start with a 2K design, we would essentially have the 4 factorial points. So now let's say we could go to the FCD design, which is the face-centered design. So here we would have these 4 points here, and you would have a center point. Now let's say even this is not satisfactory for us. We want to fit a response surface such as a fifth order polynomial or something like that. We could create something like this here, which is a subscale 2K, which means that half of this design we could create one more 2K design here. Similarly, one more path we could follow is we could go from the 2K to the 3K and the 3K to this 3K plus subscale 2K. Now for the two-dimensional problem, the 3K and the FCD are same, and so you get the same design here. So here one of the advantages is that you can start out with a simple design. You can check how your response surface is doing with respect to the actual prediction. If you are not very pleased with your model, you add these points here You either add these 4 points or these 4 points and the center points. You once again check your response surface and see how well it's doing. If it's doing well, you stop at this point, or you add further points here to sample the design space and so on. So in each of these cases, the previous points remain with you, and therefore you are simply building up this model by putting in new points. So that's why it's known as progressive lattice sampling, because you are progressively sampling the design space. So we see that the good point about this PLS method is that you could start with a very basic 2K design and add points to get the better response surface. And whatever point you started with in the design, you keep them while you keep putting on new points. Therefore, this approach is somewhat better in terms of computation. And also by putting these kind of new points, you could create higher degree response surfaces. So for example, if you were to develop a quadratic response surface with a 2K plus centered design, and you're not very happy with this response surface, you add some more points, make it a 3K design, and maybe fit it to a cubic response surface, and this result may come out better. So this is a good way to save your previous computational work and to build up your model. Now one more method is that you do not go with necessarily a deterministic sampling of the design space, but instead you generate random points in the design space and you add these points to create response surfaces which are good fits for higher degree polynomials. So one of the ways you could create this is by taking a 2K design and then putting in new points. For example, we could start with the 2K design and maybe we fit this with a second order response surface and the results we obtain are not very good. So we could add 4 more randomly selected points in the design space. Now you can select these by creating random numbers and then scaling the random numbers to lie within this particular design space. If you are not happy, maybe you want to fit a 5th degree polynomial to your model, you could create 4 more points in the design space, 4 more points, and so on. So again, this is a simple way to enhance your design and brings in a certain probabilistic component into the design process. Now one more possibility is to use gradients to enhance the response surfaces. And this essentially requires you to calculate the gradient of the function at a certain point with respect to the design variable, and the value of the gradients are also used when forming the response surface. So essentially the response surface would capture or fit your curve to the gradient value at some point. Now this method would be computationally expensive for many problems because now you are calculating the gradients with respect to the design variables, which is generally computationally expensive because you may need to calculate this with the finite difference method and so on. So do remember that these gradients are being calculated on the actual function. Now one of the things you can do is that the points where the gradients are calculated can be kept to a minimum. So one of the strategies could be is that you calculate the gradient at the center point. And this of course makes a lot of sense from a geometric perspective. A second possibility could be that you calculate the gradient at one of the points which you have selected for your experimental design. For example, if you have used CCD, you have a set of points and you find the point at which the objective function value is lowest and you calculate the gradient at that point. So this also comes out as a good choice in some cases. So in all those cases, the regression parameters are calculated by the same formula which we derived before. Now, if you are using a quadratic response surface, you have a 2D problem. Your y vector would essentially be this vector here. You would have the value of the response, let us say at n design point, but you would also have the gradients of the response at point 1 with respect to the design variable 1 and 2. Those would be G11 and G12. So these are two new things which have come into our model. And the X matrix now has this particular form where the last two rows represent the values corresponding to the gradient. So you can see that the X terms have disappeared and the X squared terms have become 2X because you have taken the gradient, and the same thing here, that these multiplied terms have one of the terms missing from them. So the last two rows refer to the gradients which have been taken. Now, typically gradient calculation is expensive, but there are situations where people are calculating the gradients as a part of the computational process, and this is often done through the concept of sensitivity derivatives. So like we discussed in some previous lecture, there are people who code in the derivative calculation as part of the calculation process for the computational model itself, and in those cases you may have cheap gradient. Also, we have discussed the technique of AD, which is used, and some codes may be there such as tapenade, which can lead you to calculate cheap gradients. And in all those cases you could develop response surfaces which have been made better by the use of gradient information. So today's lecture we discussed a few methods to improve response surfaces, to generate more points so that you can fit models which are cubic, quartic, fifth degree, and so on. And of course these kind of points can also be used to fit models such as Kriging, neural networks, and complicated functions. So there's nothing stopping you from, for example, putting in trigonometric terms to enhance your response surface. So if you feel that your problem is somewhat complicated and polynomial functions are not sufficient, you may decide to add a trigonometric series to this particular function. And in those cases you may need more and more points to sample the design space so you can get the regression parameters correctly. And in all those kind of situations it becomes useful to use one of these techniques such as progressive lattice design or probabilistic points or gradient based point. So among all these methods, probably I would say that the PLS method and the probabilistic method are very simple to implement, and they will generally be quite successful in most cases. The gradient based methods do require a lot of extra work and require that you have cheap gradients. So again, I will terminate this video here. I will see you in my next video. See you then.